also. These are two current cartoons. We had to talk about Eco engine, modified Stirling engine. First of all, what is a Stirling engine? A Stirling engine is an engine that operates on compressing and expansion gas at different temperature. Stirling engine is an engine that transforms heat energy to mechanical energy. A Stirling engine is well known for high efficiency and low reliable power. For the problem statement, our objective for the Stirling engine, we plan on creating a Stirling engine that works with a reliable power output and maintain a high efficiency at lower cost power. We have three types of Stirling engine. We have alpha Stirling engine, we have beta, and we have gamma. Beta uses its piston engine to generate power. For the alpha, for the beta, it used two piston engine to generate power. For the alpha and gamma, they are basically almost the same. They use the piston and the displacer to generate power. But the difference is the power shifting piston.
So for a literature survey, we have just a couple examples of some Stirling engines. From left to right, you see its simplicity, and as you move towards the right, they get more and more complex. So through the literature survey, here's our EcoMotor. It has 4 cylinders. This allows to create an easy and fast startup, and also produces more power. Here's a breakdown of the component design. One thing you'll notice on this EcoMotor on the top right picture is the gear assembly. Now this allows for the removal of a crank that you would see in a normal Stirling engine, this crank right here. This also sets up the piston in a daisy chain assembly. So the way you assemble the pistons is the first and third cylinder that are connected to the drive shaft are fully open and fully closed. Then the next 2 cylinders are phased 90 degrees between them, so that when you start up, you have a smooth, when it's running, you have a smooth transition. And also, one thing you notice here that you don't see in other Stirling engines is this cooling fan. Now, this cooling fan acts as the flywheel and also the cooling fan that you enclose in this enclosure, and as it produces the air, it would go up to this regeneration section and it cools down the cooling cylinders.
For the analysis of our Stirling engine, one of the few things we worked on was getting the total mass of the gas. Now, in terms of getting the total mass of the gas, there are two basic formulas we found out you could use to get this. Now, based on the parameters you do have, you could use either of these two. Now, with our own Stirling engine, what we decided to use was to use the second formula, because with this formula, we're able to get some of the parameters in here, and we're able to get some values as well that we didn't get the parameters that came with it already. So that was why we decided to use the second formula. Okay, and then after that, the other thing we worked on was getting the work done for the Stirling engine. With the work done, we're able to get the power as well. So this was the formula we basically used for this. And for our analysis, for this part of the analysis, this talks about the temperature of the regenerator. Now, the regenerator is one of the most important things when you're dealing with your Stirling engine, because basically what it does is it actually helps it's a form of an analyst. So basically, it helps in cooling and heating up of the cylinders of the Stirling engine. So basically, with the regenerator, with an effective regenerator, you get more power out of your Stirling engine. So basically, that was why this regenerator was actually very, very important to us in terms of making sure, we have to talk about it to let you guys know, how important it is to Stirling engine. Now, not all Stirling engines do come with regenerators, but if you do have a regenerator in your Stirling engine, it's much more efficient and it generates more power as well, because it makes it faster and it makes it cooler at the same time because of the temperature difference it gives. And now the other formula right here talks about the Carnot cycle. The Carnot cycle basically talks about the thermal efficiency of our Stirling engine. Of course, like Mickinson said earlier, Stirling engine is basically known for its efficiency, and to be honest, it's not really known for its power like that, but of course, one reason why a lot of companies nowadays actually run away from Stirling engine is because it produces low power. Of course, for its efficiency, we all know it gives a lot of efficiency, which we try to improve the power as well with our Stirling engine. And these are some of the theoretical data and the results that we got for our Stirling engine. Basically, the ones on the right-hand side are some of the major values we actually got. We got the pressure, the total mass of the gas, the temperature of the regenerator, the volume of the cooler, the heater, the compressor, and the expansion as well. And this was the temperature of the heater that we got in Fahrenheit and the power it actually came with. This was with this fan design, but also as we go on, we'll explain to you the other ways we actually were able to optimize the Stirling engine. And with the efficiency we got it to be 46.25% with this fan design. Now this chart right here basically talks about the temperature relationship. Now with this chart, what this is basically explaining is with the theoretical value we actually got, we're able to get the power to be 22.03 with an efficiency of 46.25. But one of the few things we realized was that with more power that was being applied, if there's more power being applied to this Stirling engine, it will actually, with more temperature that's been applied, you get more power and more efficiency. But once it gets to a certain stage, the efficiency starts dropping. So it's one of the few things we always want to put in mind when you're trying to build a Stirling engine. This was the construction material that we had in plan. If we had the chance to actually machine this Stirling engine. We had a plan of using aluminum 6061 for the power cylinder regenerator section and the power piston. For the stainless steel, we plan to use stainless steel for the hard cups, the special piston assembly, and the Boston meter gears as well.
For the experimentation plan, we plan to use a dynamometer which measures the torque generation. In order to do this, you need a weighted scale that measures the force exerted on the torque arm by the engine. And then to get the torque, you measure that force that's measured times the length of the torque arm, and you multiply that torque by the angular velocity, and you get your power output. This is a breakdown of the cost analysis. So you have your material, your stainless steel, aluminum, the hardware, which includes bearings, gears, screws, pins, sealants, everything you need for the assembly, and the machining price of $6,000. This machining price was given to us by Professor Ziccarelli, who was the instructor in the machine shop. Unfortunately, this cost is a little too high for our budget, so we were unable to machine it out of metals, but we did 3D print the whole engine, and it is functional. We just can't heat it up and run it. So what we did instead was we got a traditional Stirling engine that you can get online for about $100, and we ran multiple tests on it to see the power that it produces. I don't know if this is going to play. Okay. You see it starts up slow, and as it gets more and more heat, the RPM start to increase. So for this trials of experiment, we ran the engine using a mini hand torch, and then we got actual temperature readings of the hot and cold cylinders using a Raytech infrared thermometer. And then to calculate the RPMs, we just used a slow-mo feature on the iPhone. So the temperature of the hot cylinder, we were able to reach a temperature of 552 Kelvin, which I think it was 525 degrees Fahrenheit. Then the temperature of the cold cylinder, which is 320 Kelvin, which is about 115 degrees Fahrenheit. And then we were able to come up with a power of 0.9 watts using this Stirling engine, and an RPM of 600. Now compared to our Stirling engine, the theoretical results of 22 watts, even though ours is 4 cylinders, if you multiply 0.9 by 4, it still doesn't come anywhere close to 22 watts. One thing to keep in mind is the theoretical data was using ambient temperature, for the cold cylinder, meaning that we assumed there was no heat transfer from the hot cylinder to the cold cylinder, which we know in reality isn't true. So one way we came up with trying to reduce the temperature in this cold section right here was utilizing the cooling fan. So what we did was we came up with a few different designs and ran some basic flow simulations and flow trajectories. So this was the first cooling fan that you see in the front. It came up with a velocity of 0.6. The next fan design was just curving the fan blades and actually came up with a lower velocity of 0.5. This next fan design came up with a velocity of 0.78, and this was actually one of the fans that gave us the best results. This next one is the same fan, we just added more blades in between each one, and even though it gave us a higher max velocity, the average velocity over the trial run was actually lower. So this is just a table of each fan design and the power outputs that, or the velocity that it gave us, and obviously we chose this one. I'll talk a little bit more about what we can do with fan designs during future work.
So for the application of the Stirling engine that we actually built, what we actually planned on doing was you could actually apply it in the car. And basically how you would do this is basically by applying the Stirling engine with like an internal combustion engine. Now that way you could get more efficiency out of your car. Now the other thing you could notice is in cars like hybrid, they do use Stirling engines as well in their cars. So those are one of the reasons, one of the things we're thinking of applying the Stirling engine to. And also the Stirling engine could actually be used to power, well, our Stirling engine, I should say, we could actually use it to power like a 15 watts bulb, because basically ours would have produced about 22 watts in power, and with a 15 watt bulb, definitely it's strong enough to power it up. And for our global learning, well, one of the major reasons why my group members and I decided to take this project was because of the clean energy it actually produces. Now, everybody knows pollution is a big thing nowadays, and apparently with the pollution that it produces, with the air pollution outside now, it actually could reduce a human's life to 1 to 2 years. So we figured which ways could we think of actually, helping the human race. And one of the few things we thought about is with the Stirling engine that produces clean energy, and we figured this would be a good thing. And also it meets a no-skill requirement maintenance, and which we feel could be very useful in third world countries as well. And finally, we decided to have the manual in more than one language as well, which we think is useful all around the world.
The standard we use for our project is SAE and SME. We take for testing. This is our schedule. As you can see, like we start our project since September 29th up to here. You can see like our report take most of the time.
For the division of responsibilities, we all basically worked on the research of this project, and also I also worked on the literature survey, the formulation of design, and the analysis. While Ryan Troncoso also worked on research, like I said, and he worked on the SolidWorks simulation, prototype construction, and Mickelson also did the same with the research, and also worked on SolidWorks, material selection, and cost analysis.
So some future work, obviously the first thing would be to machine this out of metal so we can actually run it and do some experimentation work, but also the optimization of the cooling fan. So during experimentation work, we would then interchange each fan design and monitor the results we would get on this cooling of the generator section. And then, of course, couple the EcoMotor with another system put inside the car using the exhaust gases on an AC system, utilizing the heat waste of the AC system, and then putting that back into the system via mechanical work or electricity. And this is our
All right. I have two questions. The first one is, we saw your theoretical efficiency what was the original efficiency going to be? You know, your whole project was about improving the efficiency. So what was the original expected? For let's say the Stirling engine without the regenerator.
Well, we didn't really have a goal for the efficiency because based on the Carnot cycle, it all depends on how cold it can get this one. Because you can always increase the temperature through here, but the efficiency is determined by the temperature of this cooling. So I guess to answer your question, we didn't have a goal for that based on efficiency.
And the second question is, obviously your limiting constraint here was the financial aspect of the manufacturing process. Did you look at other manufacturing alternatives, metal sintering, 3D metal printing? There's a number of new technologies now that are coming out that make, especially for complex geometry, much cheaper and more efficient.
Yeah, actually, we looked into that. One of the few things we looked into was the method of 3D printing. And once we tried it, which we actually went through, like Ryan said, Professor Zaccarelli, he actually referred us to some couple of companies, and pretty much the price was pretty much close to 6,000 and some change.
Regardless of process.
Yeah, so we figured, at least we wanted to show you guys something. So that's why we decided to.
No, I got no complaints whatsoever.
And it actually works. Yeah. Well, of course you can test it.
No, that's not the question. The question is just making sure you looked at other manufacturing alternatives.
We also tried to outsource to get different companies to see if their machining prices were lower. And actually, a few said that they didn't have the capabilities to do.
Yeah, you're looking at like 6-axis for your design.
That's it.
How did you come up with your fin design for your fans?
They were mostly just arbitrary, and then during future, discussed the future optimization, we were going to then change the airfoil and run simulations to see how that would affect it, maybe change the leading angle, increase it or decrease it, and see how that would affect the flow. But these fans that came up mostly just at random, just designing it through SolidWorks.
Can you just talk about a little bit the design, kind of the overall design that you actually put into it? So, for instance, you said you just arbitrarily picked fins, and you didn't really try to meet any sort of efficiency goal. What actually were you trying to achieve, I guess, is the main thing?
What we try to achieve in this project is the power output. That's why we go like for the fence, like they're talking about, they kind of like modified. We have like some like straight, we have some curve. We already know the Stirling engine has like a high efficiency. And for like with the power flow, we can like increase, like improve the power output. That's where our goal was.
So improve power output? Is
Yeah.
that, so what?
And the gamma cell.
Again, we're going back to the original question. I think that probably the main question here. If you say the word improve, you have to start from some point, right?
Okay, basically, like Ryan said, you see, what the fan actually does is, the fan would have helped us improve the power.
Just in general, anything.
Just in general.
Anything at all in the design. What was the main goal? It doesn't have to be the fin.
Well,
Just to increase the power.
it's to increase the power.
You say increase, but increase from what to what? Did you give a value from one to the other? So increase what?
Okay, the power we got theoretically was 22, but that's what I said.
That's the final, right? That's the value that you obtained. What is the value that you're improving from?
From 22, which we got. We are trying to improve from 22 to something else. Because we knew it would have improved it, because remember, like I said, what the regenerator does is, it's basically there as a form of analysis to make it easier for the cylinders to get hot and to get cold on time. So with the change in temperature, we get more power. And that's why with the fan cools it down faster. So it gives it more the difference in temperature, which would have produced more power.
So can you quantify any of that? Yeah.
I'm sorry.
It's comparative.
Exactly.
Yeah, but you have to go from something to something, and they're comparing.
You have a slide.
So you have
very easy way to have a slide with the power.
I think 22 is what we were trying to achieve, because the theoretical value was was considering that this was going to.
That's what we're trying to find out. What's the theoretical value?
I was assuming this was at ambient temperature, which
Right.
During heating of this, there's going to be heat transfer.
What is that value?
What value?
The theoretical value you said.
Theoretical. That was assuming that was the max value we would get with this ambient temperature. Yes.
But also your problem statement mentioned efficiency, high efficiency. So
No, because they're both related.
right.
Because the way the efficiency works is the difference in temperature degrees. And also that's how the power
But how
works.
you know what's high? Again.
Oh, I think,
Understand the point you're getting at?
yeah.
Yeah.
Okay, you already know like the Stirling engine is kind of like known for high efficiency, but it has low reliable power. What we want to work on it, that's why we focus on
What is the
guidance.
value of low? What is the value of low?
What is that 22.15?
That's the power.
With ambient temperature.
Yes.
So
Yeah.
what did you get with the other temperature of the fan? With the new fan you made? Well, with the power.
That was why we wanted to get the power by getting it experimentally.
But you could.
That was our aim.
I think we're around in circles.
Yes,
We
yes.
couldn't
It's
test
fine.
it.
We couldn't test it.
Our plan was
because
to interchange the fans during
No,
the
no, I
testing.
understand
So
that.
just a general comment, guys, so that we wrap it up. When you say improve, right, you should have a number from one to another. We keep asking you what original power is or what a typical efficiency of a Stirling engine is, or what, that's all we're saying, right? You can't just put a number up there and say we improved without telling us what you improved from or